Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 1876, titled Substrings of Size 3 with Distinct Characters. We'll explore the problem requirements, break down the solution step by step, and review key concepts along the way. Let's dive in. In this problem, we are tasked with finding the number of good substrings of length 3 in a given string S. A substring is simply a consecutive portion of the string, and in this case, we are specifically interested in substrings that are exactly 3 characters long. For a substring to be considered good, all 3 characters must be distinct. This means no character in the substring can repeat. The input we are working with is a single string S made up of lowercase English letters, and the output we need to produce is an integer that represents the total count of these good substrings. Let's start with an example to make this more concrete. Consider the example where the input string S is zizaz. The substrings of length 3 are xyz, yzz, za, and zaz. Among these, only xyz has all distinct characters, making it the only good substring. The other substrings, like yzz, za, and zaz, contain repeated characters and are therefore not good. As a result, the output for this example is 1, since there is only one good substring. Now let's look at another example to further clarify. Now, take the input string S as ababcap. The substrings of length 3 here are ab, aba, bab, abc, ka, cab, abc. Among these, the substrings abc, ka, cab, and the second abc all have distinct characters, making them good substrings. The others, such as ab, aba, and bab, are not good because they contain repeated characters. Counting the good substrings, we find there are 4 in total. Hence, the output for this example is 4. With these examples in mind, let's consider some edge cases to ensure we understand all scenarios. When thinking about edge cases, there are a few interesting scenarios to consider. First, if the string S is exactly 3 characters long, the output will be 1 if all 3 characters are distinct, and 0 if they are not. Another edge case occurs when all characters in the string are the same, such as AAA. In this case, there are no good substrings, so the output is 0. Finally, if the string contains repeating patterns that include distinct substrings of length 3, each occurrence of these distinct substrings should be counted. For example, in abcap, both instances of ABC are considered good substrings and should be included in the count. These edge cases help ensure we handle all possible inputs correctly. To solve the problem substrings of size 3 with distinct characters, we begin by exploring different approaches. The brute force method involves generating every possible substring of length 3 from the input string. For each substring, we check if all 3 characters are distinct by using simple conditions like verifying that the first character is not equal to the second is not equal to the third, and so on. If the substring meets these conditions, we count it as valid. While this method is straightforward and works fine for small inputs, it has notable inefficiencies. Extracting substrings involves iterating through the string, and when combined with the distinctness checks, the overall time complexity is O(n). However, repeatedly generating substrings and performing these checks makes it less suitable for larger inputs as it can become computationally expensive. An alternative and more efficient method is the sliding window approach. Here, we use a window of size 3 that slides over the string, processing 3 consecutive characters at a time. Instead of explicitly generating substrings, we directly check if the 3 characters in the current window are distinct. If the characters satisfy this condition, we increment our count of good substrings and shift the window forward by 1 character. This approach eliminates the need to create substrings, reducing memory overhead. Since we traverse the string only once and perform constant time operations for each window, the time complexity remains O(n). This method is not only faster but also simpler to implement, making it well suited for handling large inputs efficiently. Another approach involves using a hash set to ensure distinctness within each window of size 3. Similar to the sliding window method, we move through the string with a fixed size window. For each window, we add the characters to a hash set. If the size of the set equals 3, it means all characters are distinct, and we count the substring as valid. The advantage of this method is that the hash set automatically handles duplicate characters, simplifying the distinctness check. However, this approach uses slightly more memory compared to direct character comparisons, as we need to maintain the hash set for each window. Despite this, the time complexity remains O(n), since adding to the set and checking its size are constant time operations. Among the approaches considered, the sliding window method is the most optimal choice for this problem. It strikes the right balance between efficiency and simplicity. With a time complexity of O(n) and minimal memory usage, it avoids the overhead of substring creation seen in the brute force method and the additional memory overhead of managing a hash set. Direct character comparisons make it intuitive to implement and scalable for larger strings. While the brute force approach becomes impractical for larger inputs due to its O(n)² complexity, and the hash set approach, although effective, has higher memory requirements, the sliding window approach ensures we process each character exactly once and maintain efficiency in both time and space. This makes it the most practical and scalable strategy for solving this problem. In this problem, we are asked to calculate the number of substrings of size 3 within a string S such that all the characters in each substring are distinct. A substring is simply a contiguous sequence of characters from the string. To solve this, we start with input validation. First, we check if the length of the string S is less than 3. This is because it's impossible to have a substring of size 3 in strings shorter than that. If the string is too short, we return 0 immediately, which prevents any unnecessary computations on invalid inputs. This initial step ensures our algorithm is both efficient and robust. Now, we move on to the sliding window approach to efficiently solve the problem. We define a sliding window of size 3 and initialize a variable count to 0. This variable will track the number of valid substrings. Using a loop, we slide this window across the string from index 0 to len, s3, inclusive. For each starting index I, we extract the substring s, I plus 3. To determine if this substring has all distinct characters, we convert it into a set. Since sets automatically remove duplicates, if the length of the set is 3, it means all characters in the substring are distinct. When this condition is satisfied, we increment the count variable. This process is repeated until the sliding window has covered all possible substrings of size 3, and finally, the value of count is returned as the result. This approach is built on a few key insights. First, the sliding window optimization helps us avoid the inefficiency of a brute force solution, which would involve generating all possible substrings and checking each one, leading to a time complexity of O(n)³. Instead, the sliding window processes substrings of fixed size in linear time, O(n), by iterating directly over the string. This eliminates redundant calculations, such as repeatedly examining overlapping characters. Second, using a set to verify the uniqueness of characters is highly efficient, as average insertion and lookup operations in a set are O(1). Finally, edge cases are handled seamlessly. For example, strings shorter than 3 characters return 0 immediately, and repeated characters within substrings are naturally filtered out by the set length condition. The key data structures here include the set for uniqueness checks, an integer variable count to track the result, and a loop for controlled iteration over the string. The algorithm also performs very efficiently in terms of complexity. The time complexity is O(n), because the loop iterates through the string n 2 times, and each iteration involves operations like substring extraction and set creation, both of which are O(1) on average. The space complexity is O(1), because the set used for uniqueness checks holds at most 3 characters, regardless of the string size, and no additional memory is allocated relative to the input size. Let's walk through an example with the string s equals zizaz. The sliding window starts with the substring xyz, which contains the unique characters x, y, z. Since all 3 are distinct, we increment count to 1. Next, the window moves to yzz, where the unique characters are only y, z, so this substring is invalid, and count remains 1. The process continues with za and zaz, both of which also fail the uniqueness check, leaving count unchanged at 1. At the end of this process, the final value of count is 1, meaning there is only one valid substring of size 3 with distinct characters in the given string. To summarize, this algorithm leverages the sliding window technique alongside set operations to efficiently find substrings of size 3 with unique characters. By avoiding redundant computations and handling edge cases cleanly, it achieves both optimal performance and robustness. This makes it a highly effective solution for the problem at hand. The solution to the problem begins with defining the function countGoodSubstrings inside the solution class. This function takes a string s as input and returns the number of substrings of size 3 with distinct characters. First, we initialize a counter count to 0. This variable will store the number of good substrings found during the traversal of the string. Next, we use a for loop to traverse the string. The loop range is len s 2 because we are checking substrings of size 3, and the last starting index for such a substring is at len s 3. At each iteration, we extract a substring of length 3 using slicing I plus 3. We then check if all characters in the substring are distinct by converting the substring into a set and comparing its length to 3. Sets automatically remove duplicate characters, so if the length of the set equals 3, it means all characters in the substring are distinct. If this condition is satisfied, we increment the count variable. Finally, after the loop completes, we return the count variable, which contains the total number of good substrings. This approach is efficient, as it processes the string in a single pass with a sliding window, resulting in a time complexity of O(n), where n is the length of the string. The space complexity is O(1), since we use only a fixed amount of additional space for the set and counter. This is the Java implementation of the LeetCode problem number 1876. The logic mirrors the Python solution, utilizing a sliding window approach to process substrings of size 3. The isDistinct helper method is used to check if all characters in the substring are distinct. Java-specific details include the use of substring for extracting substrings and type declarations for variables. To solve this problem, we begin by initializing a variable called count to 0. This variable will keep track of how many substrings meet the criteria of having distinct characters. For the first example, the input string is s equals zzzz, which has a length of 6. Using a for loop, we iterate over the string with a sliding window of size 3. In the first iteration, where I equals 0, the substring is xyz. Converting this substring to a set gives x, y, z, which has a length of 3. Since all characters are distinct, we increment count to 1. In the second iteration, I equals 1, the substring is yzz. Converting this to a set results in y, z, which has a length of 2. Since not all characters are distinct, the value of count remains 1. Similarly, in the third iteration, the substring za also has repeated characters, so count stays the same. Finally, in the fourth iteration, the substring zaz also has repeated characters, so count remains unchanged at 1. After completing all iterations, we find that the total count of good substrings for this input is 1. Now, let's explore a second example with the input string s equals abobcap, which has a length of 9. Again, we initialize count to 0 and iterate through the string with a sliding window of size 3. In the first iteration, I equals 0, the substring is ob. Converting this to a set gives a, b, which has a length of 2, indicating not all characters are distinct. Therefore, count remains 0. In the next iteration, I equals 1, the substring is aba. The set a, b has a length of 2, so count remains 0. Similarly, in the third iteration, I equals 2, the substring is bab. The set a, b still has a length of 2, so count stays 0. In the fourth iteration, I equals 3, we encounter the substring abc. Converting this to a set gives a, b, c with a length of 3. Since all characters are distinct, we increment count to 1. Next, in the fifth iteration, I equals 4, the substring is ka. Converting this to a set gives b, c, a, which also has a length of 3. All characters are distinct, so we increment count to 2. In the sixth iteration, I equals 5, the substring is cab. The set c, a, b has a length of 3, so count is increment to 3. Finally, in the seventh iteration, I equals 6, the substring is abc. The set a, b, c has a length of 3, so we increment count to 4. After completing all iterations for this example, the total count of good substrings is 4. This demonstrates how the sliding window efficiently calculates the result by focusing only on substrings of size 3 and checking their uniqueness. Now, let's look at one more example where the input string is s equals AAA. In this case, the string has a length of 3, which is the minimum length required to form a substring of size 3. We start by initializing count to 0. In the first and only iteration, I equals 0, the substring is AAA. Converting this substring to a set gives a, which has a length of 1. Since not all characters are distinct, the value of count remains 0. With no further substrings to evaluate, the total count of good substrings for this input is 0. This example highlights how the algorithm handles edge cases where the string contains repeated characters. The underlying process of this solution revolves around using a sliding window of size 3 to iterate through the string. For each window, we extract the substring and convert it into a set to determine the number of unique characters. If the size of the set is exactly 3, it means all characters in the substring are distinct, and we increment the count. This approach ensures efficiency, as we only traverse the string once, resulting in a time complexity of O(n). Additionally, operations like creating a set and checking its size are done in constant time. This makes the algorithm both straightforward and optimal for solving the problem of counting substrings with distinct characters. To analyze the time complexity of our solution, let's consider the sliding window approach used to iterate over the string S. The main for loop runs from the start of the string up to the point where the last window of size 3 can be formed. For a string of length n, this means the loop executes n2 times, which contributes O(n) to the time complexity. Within each iteration, we extract a substring of size 3 using slicing. Python's slicing operation is optimized to run in constant time, O(1), as it simply creates a new view of the string without copying the data. After slicing, we convert the substring into a set and check if all its characters are distinct. Since the substring size is fixed at 3, both creating the set and checking its size are constant time operations, each contributing O(1). Combining these, every iteration performs O(1) work and the loop runs O(n) times. Therefore, the overall time complexity of the solution is O(n) asterisk O(1) equals O(n). Now, let's examine the space complexity. In each iteration, we create a set to hold at most 3 characters from the current substring, as the substring length is fixed at 3. The memory required for this set is therefore constant, O(1). Additionally, while slicing the string to create substrings, Python does not allocate new memory for the sliced data but instead reuses the existing string memory. This optimization ensures that substring slicing also contributes O(1) to space complexity. Beyond this, we use a single integer variable, count, to keep track of the number of valid substrings, which also requires constant space. Since no other data structures or dynamically allocated memory are involved, the total space complexity of the solution remains O(1). When comparing this solution to a brute force approach, the efficiency gains become clear. A naive solution would involve generating all possible substrings of the string, checking the distinctness of each substring, and counting the valid ones. Generating all substrings of size 3 for a string of length n would take O(n) cubed time, as slicing each substring involves O(k) operations for a substring of size k, and k is 3 here. Checking if all characters in each substring are distinct would also take constant time for each substring, but the sheer number of substrings makes this approach inefficient. In contrast, our optimized sliding window solution processes each substring in constant time, O(1), and avoids redundant computations, reducing the overall time complexity to O(n). Importantly, this O(n) complexity holds true in all scenarios, whether the input string is entirely distinct, repetitive, or contains no valid substrings at all. The loop always iterates a fixed number of times, making the best, average, and worst-case time complexity uniformly O(n). To formally prove the time complexity, consider the components of the solution. In each iteration of the loop, we perform substring slicing, which is an O(1) operation due to Python's optimized implementation. Similarly, creating a set from the substring and checking its size are both constant time operations, O(1). Since the loop runs n2 times, where n is the length of the string, the total work done is proportional to n, resulting in a time complexity of O(n). For space complexity, we note that the set used in each iteration has a maximum size of 3, requiring only constant memory, O(1). Additionally, Python's memory optimization for string slicing ensures no extra space is allocated during substring extraction. With no other significant memory usage, the space complexity is also O(1). This confirms that the solution is efficient both in terms of time and space. One of the most common mistakes when solving this problem is neglecting to check the length of the substring in a sliding window approach. Although the goal is to identify substrings of size 3, it's important to explicitly validate the substring's length rather than assuming all substrings meet this condition. Failing to do so can result in index out-of-bounds errors or inaccurate results. Another frequent issue is relying on nested loops to generate all substrings of size 3 and then checking if their characters are distinct. While this brute force method may work, it has a time complexity of n squared, making it impractical for larger inputs. Additionally, edge cases should not be overlooked, such as strings that are shorter than 3 characters, like ub. Ignoring these cases can lead to runtime errors or invalid outputs. Finally, avoid recomputing character frequencies for every substring. Instead of recalculating counts repeatedly, it's far more efficient to use sliding window logic to incrementally update character counts, which saves both time and computational resources. Another pitfall to avoid is misunderstanding what distinct characters means in this problem. It refers to the requirement that each character within a substring of size 3 must be unique, not that the substrings themselves must be unique. For instance, both ABC and CA qualify as valid substrings because their characters are distinct, but some solutions mistakenly exclude valid substrings by misinterpreting this requirement. From an interview perspective, this problem is a great opportunity to demonstrate mastery of the sliding window pattern. Employers often use it to evaluate your ability to optimize naive solutions. Make sure to discuss edge cases during the interview, such as empty strings, strings with fewer than 3 characters, or strings with repeating characters like AAA. Efficient character tracking is another essential skill here. Using data structures like sets to check for distinct characters or hash maps to manage character counts allows you to implement solutions that are both clean and efficient. If you're asked to improve a brute force solution, highlight how you can iteratively optimize it to n using the sliding window technique. This problem shares similarities with other common LeetCode challenges that involve substring manipulation. Examples include LeetCode 3, which asks for the longest substring without repeating characters, and LeetCode 567, focused on checking if a permutation of one string exists in another. Other related problems are LeetCode 76, which finds the minimum window substring, and LeetCode 159, which involves finding the longest substring with at most 2 distinct characters. For alternative approaches, you might start with a brute force solution. This involves using nested loops to generate all substrings of size 3 and then checking each substring for distinct characters using a set. While straightforward, this approach has a time complexity of n squared, which makes it inefficient for larger input sizes. A better strategy is to use a sliding window combined with a set. By maintaining a window of size 3, you can remove the leftmost character and add the next character as you iterate through the string. This allows you to check for distinct characters efficiently with a time complexity of n. It's not only optimal but also relatively easy to implement. Another powerful variation of the sliding window approach involves using a hash map to track character counts within the current window. This method is particularly useful for solving problems with more complex constraints, such as allowing for a limited number of duplicate characters. By using a hash map, you can manage these constraints more flexibly while maintaining efficient performance. Although implementing this method requires slightly more effort compared to the sliding window with a set, the added complexity pays off in versatility. This approach equips you to handle a broader range of substring-related problems, making it a valuable addition to your toolkit for tackling variations of this challenge. Great job making it to the end. Here's a quick recap. We solved the problem using a sliding window approach, achieving an efficient solution with n time complexity. Remember the importance of understanding string manipulation techniques and optimizing for performance. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!